are here. So welcome back, friends. I have updated the syllabus, so everything should hopefully be current. I was a little distracted trying to figure out what was going to happen, but now that we know, it's all good. So I moved Quiz 5 to be due next Monday. That was originally supposed to be due today, and I had forgotten to put it up. And it's just as well because we hadn't gone over some of the stuff I wanted it to be about. So that is available on Blackboard. Homework 4 seems to have gone reasonably well, except that not everyone has finished it yet, so I can't go over it. But if you have questions as to why you missed something or why the correct answer is what it is, I'm happy to talk to you on an individual basis and answer those questions. Homework 3 revisions are due on Friday. If you are going to revise, and you only can choose to revise if you didn't get all the points. If I gave you all the points, but I still had things here and there I commented on, you don't have to revise if you don't want to. That's just sort of making sure that your product is as good as possible. If you do choose to revise, please use track changes and please leave the comments in. That way I can see exactly what I asked you to fix. It's easier on me because then I don't have to reread everything from scratch, and it's easier on you because if I miss something the first time and I notice it the second time, I can't hold you accountable if I didn't ask you to fix it. So it's a two-way street on those. Those are also due via Blackboard. I created a separate assignment that says submit revisions here. That way I can keep track of them more easily. So is anyone who's working on revisions have any questions about that? No? Okay, well, we have office hours as well for that. And homework 5 is up. So I just put that one up as well. I'll pull that up for reference. It is basically homework 3 again, except using IFA or IRT. So the idea is for you to go through the same types of steps that you went through in homework 3, test the fit of the items that you're working with, and do some describing of that fit, the reliability, and so forth. So I have, again, a list. Please write a result section. Don't put the answers after each question because I want you to have something that looks like a result section to come back to as an example. So I'm asking you to start in WLSMV because that's the easiest way to check global and local fit. Once you have decided that you like your model, then I'm asking you to re-estimate it using ML with a logit link instead of probit, and then to make tables, pictures, and some commentary. So everything that I'm asking you to do, you have an example of somewhere. So I would revisit example 6A if you have polytomous data, or example 5 if you have binary data, and you should have everything that you need in terms of that output. The only thing that you might need help with is getting the F-score distribution. I asked you to do that for homework 3 as well, but if you can't remember how, then make sure that you ask me because it's easy to get out of M+ from the graphics if you're running it in Windows. So that you have a week and a half or so to work on that, and then we're into Thanksgiving break. So note, as I had announced on the very first day of class, there is no class Thanksgiving week. I've given up holding class that Monday because between people leaving early and all the conferences I know of going on, like I've had 2 people show up before, and I'm just not going to do it. So you have no outstanding assignments to work on, so take the week off, okay? Sound good? Or do something else that's not this class. Your definition of off is all relative, right? Off from this, and then we will return for 2 last weeks of class. So I have lectures and examples posted up through Thanksgiving. We'll see if we get that far. If not, then I'll just move some stuff around and we'll make it work somehow or another. So, questions? Yes, sir?
For homework 5, is there any reason I should use the exact same data set as homework 3? So I have about 500 more respondents now?
If you want to use the updated data set, you can. The idea is to use the same items, though.
Yeah, it'll all be the same, just more responsive. I was just wondering if there'd be any benefit to being able to compare directly those 2.
It would be informative, I think, to see to what extent the problems you encountered go away when you fit a writer model. But if you're looking to do something publishable and you don't want to have to redo it twice on different samples, just go with the bigger sample. Yep. Right. Any questions, comments, other things? Are we awake? Yeah, more or less? Cheers. Yes, I'm holding up a Diet Mountain Dew can for those of you watching at home. I'm not so tenured that I show up drinking to work. Not yet, anyway. We all have goals. All right, so we're talking about invariance. Remember that? So let's do some vocabulary review because that's really the only new concept here. Give me a synonym for invariance in this context. Equivalence. Yeah, it's the opposite, I guess, an antonym or a synonym, right? Words that fall into this category. So measurement invariance, structural invariance, factorial invariance, measurement equivalence, and what is it going to be called when we switch back to IRT and IFA? Three-word phrase. Starts with a D. Differential item functioning. So the idea generally construed is whether or not your measurement model parameters are the same across some type of comparison. So it can be different groups of people, it can be different occasions, it can be different repeated measures conditions, it could be different respondents. So if you have like a teacher report and a self-report, something like that, you could see whether the items function the same way across some kind of different condition. So invariance means they're the same. Non-invariance means they're different. And for reasons I am not privy to, it's always non-invariance, not just variance, as you would think, right? Non-invariance seems a little ridiculous. But non-invariance is the same thing as differential item functioning. So whether it's different or the same is the big question. If you're writing for a non-technical audience, I would go with the test of measurement equivalence because people know what equivalence means outside the context of statistics. So what parameters are being tested depends on the type of measurement model that you have. All measurement models can be tested for invariance. So if we're in the world of CFA, each item has up to 3 estimated parameters. Remember what they are? Intercept, loading, and residual variance. Yes. Is anyone else here? Yes, thank you. Intercept, loading, and residual variance, right? So each of those has a special name. So in the world of invariance, what's it called when we start off with the same type of factor model across both, let's call it groups to start with? Special name starts with a C. Configural, yes. And so that just means like if you fit 2 factors, you fit the same 2-factor structure in each group. It could differ a little bit, like one group could have an extra residual covariance or 2, one group might have an extra cross-loading, something like that, but generally speaking, the same basic structure needs to fit in each group. Otherwise, game over. It does no good to see if your items relate to their factors in the same way if the factors aren't the same. So configural is step 1. From here, in terms of absolute fit, every further comparison is done with the goal of making the model fit, not worse. We should be able to make the group share parameters across groups and have there be a non-significant change in model fit, a non-significant decrease. So after configural, next step is what? So let's go, what are we testing first? I'm going to start calling on folks. Tyler, I'm calling on you. Slopes, okay, otherwise known as? What's the synonym for slope? Loadings. Give me another one. There's one more I can think of. Okay, would you like to phone a friend? Yes. Okay, who would you like to phone? Okay. No, did he point to Katie? Sure. Okay. Yep, okay. It's a general term. There's 2 item characteristics that show up across models. It shows up in classical test theory as an item total correlation. It shows up in CFA as blah, which is a No, item things. And it's actually called this directly as an A parameter in IRT. No, we're getting warmer. Starts with a D. Other one. Good guess, but that's the wrong T word. I thought I heard it. Lucas, did you say it? Discrimination, yes. So generically, items differ in these models in their difficulty and their discrimination. Discrimination is the idea of how related the item is to the trait. In a CFA model, that idea is instantiated as the item's loading, or slope, or discrimination. Yes, vocabulary, because you will see that different audiences talk about these things with different words. So I want you to know all of them. So yes, when we test the loadings / slopes / discriminations in a CFA model, that step is called. Who wants to try? Starts with an M. Did you say matrix? No. Metric, yes. Otherwise known as. Weak. Yes, weak is the synonym for that. So the idea of metric then is are the loadings equivalent across groups? In other words, is the only reason for differences across loadings differences in factor variance? And this step is important in terms of the definition of the factor. So if you're able to constrain the loadings to be equal by freeing the factor variance in the alternative group to pick up all of those differences to make it proportional, then you have greater confidence that the meaning of the factor is the same. So let me draw briefly. I'll narrate while I'm drawing because I'm faster at it. So if I have, let's say, a 4-factor model in group 1, and here's my 4-factor model in group 2, and in group 1, my loadings go 0.5, 0.6, 0.7, 0.8. I'm just using standardized numbers to make it easy. And in group 2, my loadings go 0.8, 0.7, 0.6, 0.5. If this model held, I would say that we've achieved configural invariance because I have a factor that is supposed to be responsible for my 4 answers here. However, this model would likely fail metric invariance because which items are relatively most related to the factor differs across groups. So if I were going to try and interpret this factor, if I came with more of a data-driven perspective, I would think it has more to do with the 3rd and 4th items in group 1 because they have the standardized loadings of 0.7, 0.8, whereas in group 2, it has more to do with items 1 and 2. So that's where you get into sort of conceptual difficulty when metric fails. It's like, well, what is the factor? In contrast, if I had something like this, where I'm erasing group 2's loadings, and I'm changing them to be, let's go, 0.3, 0.4, 0.5, 0.6. So if group 1 goes 0.5, 0.6, 0.7, 0.8, group 2 goes 0.3, 0.4, 0.5, 0.6. Is metric invariance going to hold? What do you think?
Yes. Relative to one another,
They're proportional. Yeah. So a difference in factor variance could have caused this systematic difference that shows up equally across loadings. Yes, sir? What that means? So given the standard deviation of the factor, these loadings are the expected change for a 1-unit standard deviation of the factor. If one group has a smaller standard deviation, then you would end up with a larger change because of that relative to the other group. So if you have loadings that are smaller, it could be because that group has more variance than the other group in their factor. And so all of these tests that we're doing are on the unstandardized factor loadings. And those are relative to the scale of the factor. So as an example of that, in the example we started working through, the configural model had loadings that looked like this across groups. So this is example 7A. I am on page 2, and this is a picture that I made of the loadings from the configural model. So at this point, both groups have a factor variance of 1. It doesn't mean that both groups are on the same scale. It means they're on the same arbitrary scale that's within group scaled. So in this case, it looks like the items are more related to the trait in women on the whole. It looks like the red bars are bigger than the blue bars for most of the cases here. But it turns out that is because after we constrain the loadings to be equal, women have less variance in their factor. So once you set the loadings to be equal, you have to allow the factor variance to pick up whatever differences were there. So by freeing the factor variance in the women's group, it's free to be something different than 1, which is the reference point for the model. The men are what's identifying the model. The women's factor variance is 0.86. So the reason why the loadings were different on the whole is because there's a difference in scale, what the loading is multiplying by. So now they're all being held the same, and whatever difference was there is supposed to be being picked up by the factor variance instead. So in terms of the code, the configural model starts with everything different for each group, and then we slowly add constraints step by step to make the alternative model, which is the men here, match the women. So at the configural stage, both groups are separately identified by factor mean 0, factor variance 1. At the metric stage, they are sharing an identification that comes from the man here, the reference group, factor mean 0, variance 1. By fixing the loadings to be equal, we then have to free the factor variance, and we would do so for every factor in the model so that any differences can then be absorbed at the factor level. How are we doing? Remember this? Maybe? Yes, sir? No, but I'm trying to remind myself who's the reference here. The women are the reference? Oh, that's why. I was working on your example 7C where it's backwards, so I think I misspoke. Women are the reference. And so the men are the alternative group. They have the variance that's lower. So I'm saying it backwards. Thank you for catching that. Yes. I try to stick with reference and alternative because these things are arbitrary. The reference group is always the one that identifies the model, and then the alternative group is the one that gets the factor variance and mean free as you constrain loadings and intercepts. So yes. But point being, differences in factor variance is one of the reasons why we may have differences in loadings. I think I said it backwards in terms of the direction because I was thinking about the other example that I was already working on. My bad. Okay. So configural, metric is loadings. What happens if we test the loading equalities and the model fits worse? Give up and go home? No? What do we do? Try to find out why? Yeah, so in this current example, we didn't have to try and find out why. As I said, it was a textbook example. We tested 8 loadings, all 9 loadings simultaneously, a total of 8 degrees of freedom once you free the factor variance, and the difference in model fit was non-significant. But if it were significant, it's our job to figure out why. And whenever you are dealing with some kind of covariance matrix, so in the world of CFA, when you have an actual covariance matrix, as well as in the world of limited information, WLSMV, when you have a polychoric covariance matrix. So long as you've got an answer key, so long as you've got an H1, you have voodoo to help you figure out what you've done wrong. And in this case, I still say voodoo because it's completely data-driven and atheoretical, but it's not the same type of problem as when you're initially fitting the model, because these are constraints that you put on the model yourself. It's going to tell you which ones are hurting your fit. Why it's that item as opposed to another one, I have no idea. That's the part where you have to figure out to what extent this would be expected based on the content and replicable in other samples. So if you're able to constrain at least some of the loadings to be equal, then we have a middle ground between non-invariance and equality. What's it called? Starts with a P. Partial, yeah. Partial metric invariance is what I would call that, so long as it's not full. So then what's next? We do configural, we do metric, which is loading / slope / discriminations. Then we have what else? Scalar, which is synonymous with strong. Yes. I don't know where these things came from. Someone's going to say this to you, and I want you to be like, well, I wouldn't call that weak. Like, oh, no, that's a thing. Okay, gotcha. Strong, scalar. What is that testing? Intercepts in this case. So it's the location parameter of the CFA model. And it's not testing item means, it's testing item intercepts, right? So if we go to the same type of idea here, what's already on the board instead of loadings, if we call these numbers intercepts, if this pattern still held, if you have 5, 6, 7, 8 for your intercepts in one group and 3, 4, 5, 6 for your intercepts in another, this pattern could be perfectly explained by a factor mean difference of 2. So the idea behind intercept invariance, scalar invariance, is that after controlling for the factor, at a factor score of 0, all groups should have the same expected response. It doesn't matter if you're a man or a woman or whatever. That's the idea. It's not that men and women have the same amount of the trait. It's that once you control the amount that they have, they answer the items the same way. And so this was an instance in which, in our example, we constrained the intercepts to be equal in the alternative group. We then freed the factor mean in the alternative group so that we allow differences in the trait. And in your textbook, because the overall test was non-significant relative to metric, they decided that was good enough. I went and looked at the voodoo to see if there were any particular constraints that were causing problems, and it turned out that item 7 was responsible for fully half of the change in fit. So I opted to free the intercept for item 7, refit the model, and allow the groups to have a different intercept. So it turns out that the reference group women had a higher expected response on item 7, even if they had the same level of depression as the men. So at a factor score of 0, a woman would likely be answered 3.8, whereas a man is likely to answer 3.5. Given the sample size, that is a significant difference. On a scale of 0 to 9, a difference of 0.3 may not be that practically meaningful, but it is significant from a statistical point of view. And then last but not least, what's our third parameter in our measurement model? Feel free to read from the board, or the screen, as it were. Residuals. Does this have a special name? Strict. Yes. As I had said before, it's debatable whether or not this really matters. It just means that the amount of, not the factor variance that you have in an item differs across groups. construct irrelevant variance. There's been some simulation work suggesting that matters in certain circumstances. I think most of the world's like, they can't get too excited about it. But in this case, it held. And I think this is where we had left off. Is that right? More or less? Okay. So, metric loadings, scalar, intercepts, then residual variances. That's measurement invariance. Those are the steps that are necessary in order to say that you have basically the same factor being measured by your items across groups. There is a very sharp delineation between those three steps and what follows. What follows, the new part that we're going to do, is called structural invariance. This is the idea of testing factor parameters, factor variances, factor covariances if there's more than two factors, and factor means. In contrast to measurement invariance, where you're hoping that it's the same, it may be a good thing, a bad thing, or whatever if structural invariance doesn't hold. Structural invariance is oftentimes a hypothesis that you want to test. Are men and women different in their latent levels of depression? Are men less variable than women in their levels of depression? These are questions you may want to know. In order to get to the point where you can answer them validly, though, you have to have at least partial measurement invariance to say, no, it's not just the items, it's the trait that differs. So if you were planning on doing some kind of structural equation model, looking at gender differences in depression and how depression relates to other stuff, this is the point where you would likely stop. You would have your measurement invariance model. You would let men and women differ in their amounts of the factor and in their factor variance, and then you go about testing other hypotheses. For instance, does the path from depression to, say, anxiety differ between groups? You can do invariance constraints on that path to see if that relationship differs. It wouldn't be necessary to have structural invariance to answer any kind of substantive questions about the factors. If you want to test structural invariance, though, here's how you would do it. So we did the residual covariance, then we did fix the factor variance back to 1, see if the model fit gets worse. At this point, the factor mean is still allowed to differ between groups, and we get a p-value directly on it to test whether or not the factor mean differs between groups. But you can test it formally with a -2 log likelihood difference, and we end up with the same conclusion. A p-value of 0.27 is to whether or not the factor mean differs between groups, which is the same thing that we saw in just the parameter for the factor mean, which is the difference. So in this case, it looks like men and women do not differ in their factor means nor in their factor variances, and that's the end of the story. So one thing that I get a question about in this context is the difference between this type of model and just putting gender in the model as a box. So I'm going to have to break out paint here. Let's see, let me find it. Here's paint. That way the folks at home can see my lovely drawing abilities. So I'm going to put a box here. Do you remember what boxes are for in our notation? What goes in boxes? Not factors. Boxes are for what? Observed variables. Yes, real things. So I'm going to make a G for gender. Oh, that's not bad. And what goes in circles? Latent things, not real things, unobserved things. And I'm going to make a sad face for my depression measure. So what is the difference between what we just did and this? Yes, sir? the invariance testing process as to whether or not there are gender differences in the measurement of depression as well as the mean invariance of the latent factor. So what's the difference between this type of picture and what we just did? Or did we do this? Direction of the arrows? Does depression cause your gender? Probably not. I think some sort of hormone in the 4th month of pregnancy does that, right? If I remember correctly. Or excuse me, your biological sex, your gender is a whole separate thing. But we're sticking with gender for right now because it's a simpler world back when this textbook was published. So the arrows going the right way. Gender is a predictor of depression in this model. What's the difference between invariance testing and this idea? It's tricky, huh? Is Mayumi still in Japan?
Yes, she could be listening, but I'm pretty sure it's like 2 a.m.
Okay, so I really hope she's not listening, but maybe if she's listening at some other point, because this is her dissertation, and these are issues that we've been talking about. So here, let me finish drawing my little picture here of this is my latent factor of depression, and dot, 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 dot. Here's my 9 items, and each one has a box for my observed variable. There we go. So this type of setup is what's known as a mimic model. Multiple indicators, multiple causes. It is technically possible to allow a gender mean difference in the latent trait, but at this point, we wouldn't know whether or not that mean difference is because of differences in the way the trait relates to the items or differences in the trait itself. This type of setup assumes, without testing, measurement invariance. So in order to be able to legitimately look at differences as a function of any type of group in a latent trait, ideally you'd want to test for measurement invariance first to rule out that as another confounding reason for the differences. But you will also occasionally see people try to test measurement invariance in this context by additionally drawing paths, these are regressions, to the observed items besides the trait. So this would allow gender-specific effects on the intercepts above and beyond the factor. It's kind of a cheaty way to test invariance. But what can't we get out of this type of model? A couple things. I know we haven't talked about SEM yet, but have you ever seen gender going to a loading in any of these pictures? No, not really. Gender differences in the variance of the item residuals? Nope. Gender differences in the variance of the trait? Nope. So this type of approach where the box is inside the model as a predictor allows mean differences only. Mean differences in the factor as well as potentially mean differences in the item intercepts. It's not a true invariance model. That being said, the invariance model already gives us what this path would be that we're interested in. The difference between genders in the latent trait is the factor mean in the model for the alternative group. So the factor mean is 0 for identification in the reference group. In the alternative group, the factor mean is estimated, but what it actually is the difference from 0. It's a factor mean difference. So that path from gender to the latent trait would be this minus 0.094. That's what it would be. It's the same. But this invariance approach allows other tests that putting the box in the model does not. It allows tests of the loadings, tests of the factor variance, and tests of the residual variances for the items. Does that make sense? Now, question? No? Good. Now, what if I change this? And I am going to use another variable of Mayumi's. So you see how I did that? Age. Maybe older people are more depressed or less depressed. I don't know. You can do this, right? This is a structural equation model. You can see whether or not there is a linear or potentially nonlinear effective age on depression, and that path would give you the change in the latent variable for a 1-unit increase in age, so per year, per week, whatever your time frame is. Now, how would I do that in an invariance analysis, a multiple group invariance analysis? Yeah, the correct answer is, well, you got 2 options. You got a guess?
No.
Okay, fair enough.
No, sorry.
No, please, go ahead.
Okay, so the age, the arrows that are pointing to the observed variable,
Mm-hmm.
so how is there anything left to control for in a latent variable if you're already controlling for age and all of the observed variables? The observed variables are loading onto this. Like, aren't you just double controlling? How does that, like, change?
It may not be identified in some cases because, yeah, it's redundant in some sense. But the idea is that there are additional reasons why people answer those items differently as a function of age besides depression. So if you think about, like, I have trouble sleeping is a common depression type item, or I lack energy. Perhaps an older person may say, yes, I lack energy, and it has nothing to do with depression. So after controlling for the effective age on depression, is there a supplemental or unique effective age on the particular items that has nothing to do with the trait? So it's trying to take that, not the factor variance, and sort of carve into it at the same time. That's the idea. But it gets tricky when you don't have that many items. Like when you have 3 items for a trait or something, then it gets hard to think about what's trait and what's not the trait when you don't have a lot of information to parse those things apart. So yes. But do you have a guess how we would do this in invariance framework?
Invariance framework is
like putting them in groups, like men and women, or control treatment, or something like that. Set an equal.
No, I don't have to guess that. I mean, you could.
It's tricky, huh? Can you guess what I told Mayumi to do? Cut it up! You have young people and old people. Congratulations. Is that a good answer? Depends. Do you want to graduate? It's a great answer. Do you want to do it the right way? There is a more righter way that has become, I'd say, is starting to enter the literature for those sorts of problems. Did I put that article on your reading list? Let me see if I can find it. I don't know if I did or not. I may not have because it's hard. But if anyone has that problem and they want to learn how to do it the right way, basically what you have to do is create a linear model for each of your slopes by which you would allow model constraints for age as a continuous variable to have a continuous loading onto the loading. I have tried to play around with it. I have been unsuccessful in getting it to actually estimate on real data. But I can give you some references. It's Dan Bauer and Patrick Kieran's work out of UNC. They have some models looking at this in the context of IRT. I can't remember their acronym, but it's a mouthful. That's all I know. MNLFA or something like that. Manipula, I believe, is how you pronounce that. But yes, All of this invariant stuff is all neat and tidy so long as you have groups. Anything that is not a group either is way more complicated or it has to be cut up to become a group. And there's not a great solution to that, unfortunately. And let's see, structural invariance and words. See, words. That's all the things I did. Yes, sir. Absolutely. It just gets to be a bigger headache the more groups you have. Because then there's more possibilities of how you can have non-invariance. So let's say that you have 4 groups. You could have, for a given parameter, 1 could be different than 2 or 3 or 4. 1 could be different than 2 and 3 but not 4. 1 could be different than 2 and 4 and not 3, et cetera, et cetera, et cetera. So there's a lot of permutations that you may have to wade through as to the exact source of the differences. Other questions? So this is a nice, happy, tidy textbook example. Do you want to see what this looks like in the real world? Why not, right? So let me open up example 7b. I'll save my crappy drawing because I may need to refer to it later. And I will shut that spreadsheet down and get a new one. All of these examples come with spreadsheets for model comparisons and/or making pictures. Okay. So example 7b is another CFA example. So we're still dealing with measurement invariance of loadings, intercepts, residual variances. However, this is in the context of longitudinal data. There we go. And let me freeze frame, freeze panes. There we go. All right. So these are real data. They come from the dissertation of a student at UNL quite a while back. I want to say 2009, 2010-ish. The good news is that he has the done kind, he had a postdoc, and now he has a job, and he lived happily ever after. So just keep that in mind when you see this invariance model fall apart piece by piece by piece, because this is often what happens, unfortunately. Don't make that face. This is real data. So these are patients with severe mental illness in a psychiatric rehabilitation center. That's the setting. So there's all kinds of messiness here that I allowed him to go, not paying attention. Like ratings were taken from different hospital staff. People were in the hospital for different lengths of time. They were different ages. They had different diagnoses. All of that we're just ignoring, right? We're treating them as some sort of homogeneous sample. That way he has the done kind. So we're working with 3 occasions of data. Time 1 was when they were admitted to the hospital. Times 2 and 3 were approximately 6 months later. We're pretending that those times are balanced, that they were all exactly measured at the same times. That's another thing that's probably not true. These are 6 subscales of basic types of functioning, social competence, social interest, and personal neatness, which more is better, and negatively oriented measures in which more is worse of psychoticism, motor retardation, and irritability. So I took the last 3 and reflected them by multiplying them by -1 so that all of the variables went into one direction. The idea that this latent trait is some sort of level of functioning, let's just call it that. I am not a clinician and I'm not going to pretend to be, but we'll just call it that. Can I say that? Functioningness? Can we please make that up? Why not, right? So, and because I'm not personally invested in the names of these things, I just named them variable 1, variable 2, and variable 3, variable 4, and variable 5, and variable 6, and then I have variable 1 at time 1, time 2, time 3, and so on. So we're already, in addition to the complexities of the sample, we're using subscales. Now, what does that mean from an item measurement perspective? What am I assuming without testing and using subscales as items? They had good alphas, by the way, just so you know. Tau equivalence, bigger problem than that. Unidimensionality of each one. Not only do they measure everything equally well, they measure the same thing, and uncorrelated errors as well. Now, why did I allow him to do that, in addition to just wanting to graduate? Sample size. He has 151 people. No way was a second-order measurement model where each of these subscales has like 20, 30 items, and then there's 6 subscales over 3 occasions. No way is that going to work on 151 people. So I allowed him to add shit up and then fit the models to the subscales because I was reasonable and I wanted him to graduate. So those are all the caveats that go into this analysis before we even get started. So this analysis is going to be different because these are dependent data. So previously we worked with the multiple group format because the men and women were independent. Had the men and women been dependent, had they been in a relationship or siblings or families or whatnot, or in this case, the same person repeatedly measured over time, the model has to look different. So what we're going to end up doing is a model that looks a lot like where we started, where there's only one model, and all 3 occasions are represented as different factors. So I have 6 items, in this case, 6 subscales by 3 occasions. I have 18 variables that I'm working with simultaneously in one analysis. So in the setup here, there's no group variable. There's only this part here, define, is where you can do math to make new variables and that kind of thing. And here is my configural invariance model. So time 1 is the name of the factor at the first occasion, time 2 and time 3. I have my loadings all estimated. I have my intercepts for each variable for each occasion. I have my residual variances for each variable for each occasion. Each occasion's factor has a variance of 1, so each occasion is separately identified. Each occasion has a factor mean of 0. And because these are the same people over time, I have allowed all possible covariances between the 3 factors. So there's 3 possible covariances. This is a shortcut way to refer to all of them. If you put a list of variables and then with and then the same list, it does all possible combinations. So the same thing happens on the last 6 lines. Those are correlations between the residuals of the items across time. This is the idea that even after controlling for one's general tendency on the factor at each occasion, what you said on item 1 the first time is likely to be related to what you said on item 1 the second time and the third time. So in longitudinal invariance, any kind of dependent grouping, all this part down here stays the same always. There's no changing it. We assume that people are related across time. We assume that what you said to a particular item will correlate with what you say next time, independent of the factor. If the latter is not true, you could remove them to save parameters, but this is usually just sort of a default thing that people start with. So you may see sometimes people do longitudinal investigations in a multiple group framework. You cannot do that. It would be the same thing as not allowing covariances between the 3 factors. If you set it up as a 3-group model instead of one model with 3 factors, you're not allowing where you stand on time 1 to be related to where you stand on time 2 or time 3, whereas this model explicitly accounts for that. So it has to be done this way if you have dependent groups. Okay, with me so far? What if I were to have different items at each occasion? What if I only gave the 6th variable at time 1? Should I get rid of it? Don't have to. Leave it in. You can't test invariance if it's not measured repeatedly, but you can allow the time 1 factor to be defined by unique items in addition to the common items. That's the spirit of the linking design. So in this case, we're not necessarily expecting the construct to change over time because this is a relatively short period, But if this was taken over many, many years, you might have a common set of items across time, but then supplement with easier or harder items as people change. The easier and harder items invariance wouldn't logically apply, but it would apply to the common items. So you don't have to have the same items over time, but you have to have at least some in common in order to be able to link the traits so that you can say that it's the same trait across time. So we're estimating all loadings, all intercepts, all residual variances. All the factor means and variances are fixed for identification. We're estimating all factor covariances and residual covariances for the same occasion. Okay, questions? So this is as good as it gets, right? Let's see how good it is. 75 free parameters. Where'd that come from? Do a little review, too. How many items do I have? I'll go up here to use variables so you can see. How many things am I listing here? Not a trick, I swear. 18. 6 indicators times 3 occasions. What is 18 times 3? Not a trick. 54. So how did I get all the way up to 75? Well, I got to add 3 more covariances among my factors. That's 57. And the rest of it is all residual covariances. So it's the covariance for the same item across time within each item. So that's where the rest of them come from. So what do you think about the fit of this model? That's generous. It's not great. But he spent like a month trying to make it better and couldn't come up with anything that would make it better. And I said, you know what? Go ahead. Just go with this, right? So it's not great. It's not going to get better in an absolute sense. However, RMSEA could get better as the model gets more parsimonious. And we'll see the CFI have the same sort of tendency. So here, then, we're going to foreshadow. Here are my factor loadings for each of the items. We're looking for any kind of proportional difference that could be held due to the factor variances. I don't know about you, but I'm not seeing any. But I do see something that sticks out like a sore thumb. Do you see what I see? This one. It looks like this item is way more related at time 1 relative to where it is at the other ones. Spoiler alert, that item is going to be non-invariant in terms of the loading. But it's item 1. So what would M+ do to it by default had I not intervened? What does M+ do to your first item's loading unless you tell it otherwise? And every other SEM program in the world too, by the way. They fixed the loading to 1. Yeah. So if you went with the default way of estimating these models, you would be constraining this item's loading to 1 here, here, and here for identification. And that would screw up everything else because it's not invariant. So I'm going to end up using item 2 instead, as I recall. At least that's one way that you could do it with if that was your goal of keeping the factors so that you can estimate their variances if you wished. But here's what we end up with. for the configural model. Next up is metric. So now, rather than constraining across groups, I'm adding the same label across time. L1 to L6 shows up at time 1, time 2, and time 3. So I'm constraining item 1 to have the same loading across time, item 2 to have the same loading across time, and so forth. In so doing, what do I have to do to free something? What gets freed when the loadings get fixed? Adrian, what do you think? I know you want to speak. I can see it. The variance of what? Yes, the factor variance. Very good. These ones right here. So time 1 still has its factor variance fixed to 1 for identification. Something still has to be fixed to 1 for this to work. But time 2 and time 3 have their factor variances free so that they can absorb whatever proportional differences there would be in the loadings. In just staring at this model output, do I know if putting those loading constraints on hurt? Does anything on the page tell me that, straight up? Not in CFA. This is where you're going to have to do your own model comparisons using your HO scaling factor, and your new degrees of freedom. Thank you for that sound effect. So here it is, 10 degrees of freedom, because I constrained 12 loadings, but then I had to give back 2 factor variances. P-value of 0.04, let's call that significant today. What does that mean? And feel free to read from the screen. Want to try it again, Adrian? It's worse. Yeah, worse? Question mark? Significant means yes, worse. So no, I can't constrain these loadings. At least not all of them at one shot, right? I'm testing a whole bunch of things at the same time. So let's see what the voodoo says. I printed out just the ones that are relevant for what we're doing right here. So it says, I would like to have a new loading for variable 1 time 1 on time 1. And you're like, variable 1 time 1 is already on time 1. Huh? No, it wants to be more on it, meaning let that one go. It's the biggest change. The expected parameter change, second column there, says its loading wants to be bigger. So let's do that. So I changed the label for the first item at time 1 to be unique. Doesn't matter what you change it to, just adopt your own system so that you can follow it. I have L1A for alternative instead. L1 is still holding 2 and 3 together. So time 2 and time 3 still share a loading for item 1. It's time 1 that allows it to be different. There's 2 model comparisons that are relevant. We may want to know if we're headed in the right direction. So relative to the last model that we had that was broken, did changing that one thing help it? So that's the first thing that I asked for. And yes, chi-square change of 7 on 1 degree of freedom. So yes, we're headed in the right direction. Freeing that one loading made the model fit significantly better than the full metric invariance model in which all loadings are constrained. Now, is freeing just that one loading enough? That's the next one. So now we're going back to our original reference point, configural, and seeing if our partial metric model fits, not worse. And survey says, dun, 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 totally non-significant. You win. So it looks like the rest of the loadings can be constrained equal across time, which one might interpret as the same factor, this items measuring the same factor over time, with one small exception. And that's highlighted here in bold on the output. Item 1 appears more related to the factor at time 1 than at the other occasions. Item 1, again, was social competence. So in addition to making up some reason why you would have expected that in your discussion section and citing other people's studies where they might have found something similar, I also should probably say something in the limitations about this. Before I get super excited that all of my loadings were invariant, which means my same factor is being measured over time except for one, I need to fess up to something. Maybe what do I put in my limitation section? Besides all of I ignored everything about the sample that was complicated, besides that. I will give you a breadcrumb. 151 people. Lots of missing data, by the way. Another thing I need to fess up to. Think about power. What are we hoping for in terms of a null hypothesis? Lord help me, I'm going to take you back to intro stat. Reject or do not reject, right? Isn't that what they told you? These tests are hoping for what? Which one? Invariance? Do we want to reject? If you want to say that the same thing's being measured over time, do you want to reject? You want to retain. Can I say that? I think I used to get yelled at for, no, it's do not reject. No, it's retain, whatever. Yeah, you want to retain the null. And anytime you want to retain the null, what do you have to cry? Someone's going to yell at you unless you talk about, starts with a P. Give me a P. Give me an O. Give me a W. What's my best W? Give me an E. Can't quite do that. I need some extra people. And then R. Yeah, I know. You expect me to do cheerleader letters backwards for you people? My goodness. Okay, fine. P, O, W is the same. E, R. What's that spell? Power. Thank you. Yes. Do I have sufficient power to reject the null that these things are equal? 151 people? Probably not. To answer that question with more than just probably not would require maybe a post hoc power analysis. You could see how many people it would take to detect a difference of whatever size. That could give you some indication in terms of planning a future study to look at this sort of thing. But yes, before we get too excited that we found invariance, we have to remember we have crappy power with which to detect non-invariance. It's backwards from how you're normally used to thinking about it. So that's the caveat that we have to remember. So here's a picture then of the intercepts forthcoming. So each of these items has a different intercept. 4, 5, and 6 have much lower intercepts because they're backwards. So the absolute amount of each one shouldn't bother you, but it's all about how they change relative across time. And if, in this case, higher scores is better, so if people are growing in functionality, let's call it functioningness over time, we should see these happy little bars get taller over time. Do they? Sorta. At least 1, 2, and 3 kind of look like they do. 4 looks like it goes backwards a little bit. 5 goes backwards a little bit, and 6 grows. So in my eyeball test here, my visual analysis, I can tell you longitudinal invariance is maybe not going to go so well for these intercepts. There's likely something else that is going to be causing mean differences in these items besides just the trait. All right. So let's try it out. Intercepts. Now you can see why I wrote them the way that I did. I1 is going to be the intercept for item 1 for 2 and 3, but not for item 1. Do you remember why that is? Why did I do it that way for item 1 when I didn't do it that way for 2, 3, 4, 5, or 6? What's special about item 1 time 1 that we just found like 5 minutes ago before I started doing my cheerleader things? And I was never a cheerleader, thank you very much. I was a pom-pommer. That's dance team. We were way cooler than cheerleaders. Just saying. But what's different about item 1 time 1? Is its loading broken? Yeah, so it got kicked out. Whenever you have different loadings, the intercepts can be different for that reason alone. So it's like a tournament. Item 1, loading, broken at time 1, so its intercept got kicked out of the tournament. So we're starting by just constraining the intercepts for 2 and 3 as a consequence. All of these other items are still up for grabs. And in trying to make sure that you understand your code, neat code with spacing is your friend. Because I took the time to space these out, I can eyeball these quickly and know which ones are constrained across 1, 2, and 3. And I would encourage you to do the same when you're doing this in practice. So we'll get to pick up the exciting conclusion of scalar invariance next Monday. So any questions before we adjourn? All right then, bang bang. Class dismissed. Office hours start now. Let me know if you need anything as you're working on revisions to 3 or otherwise.